Hello, dear friends. In this video, I'll show you step-by-step how to build a digital video link based on an IP camera. This video is for the onboard component air unit. We'll be using a $10 IP camera as the FPV camera. It comes without a lens or PoE cable. It comes with factory firmware, which we don't need. We'll be flashing the camera with OpenIPC firmware. The camera has UART pins for this purpose. OpenIPC is an open-source project. The system is based on the Linux kernel, allowing us to work with the camera as if it were a single-board computer. We'll use this USB modem as a VTX video transmitter. We'll connect it to our camera via USB port. This thing will operate in monitor mode and simply throw packets into the air without waiting for confirmation from the receiver. These two devices are sufficient for the onboard air unit. The whole thing costs $19 plus $3 for the cable and lens. We'll use the same modem, a laptop running Ubuntu, and the appropriate software as a ground station. I'll also show you how to set it up in this video. For now, I'm using it like this. Everything should work in test mode within the apartment. But if we want to increase the range, there are connectors like these on the USB Wi-Fi modem board. I understand these resistors are desoldered and soldered onto IPEX connectors, which are used to connect antennas. You could connect antennas like these here, for example. Well, that'll need to be tested. I haven't tried that yet. I ordered the camera here. I already had a cable and lens, so it arrived in this box. I screwed on the lens and plugged in the cable. It's a standard Ethernet cable, but there's also a 12-volt power connector. These connectors fit here. I connect the patch cord and power from this power supply. I set the 12-volt and turn on the power. I connect to the camera, thus checking that everything is working. The IP address for connection is on the camera seller's website, and the login is listed there. I connect. Great, everything works, which means the camera is working. To reflash the camera, we'll use the UART connector. It has a bootloader installed to boot and update the camera. I've already ordered these cameras. They come with a password-protected bootloader. The bootloader can be accessed via UART. For ease of connection, I'll make a connector like this and solder it to these contacts. This is a ZH15 connector. I'll solder these wires to it. I'll follow this diagram. I want a convenient plug-and-play connection. All that's left is to solder the wires to the camera. I'll be connecting via USB TTL converter. Don't forget to install the drivers for it. It's simple. Plug this into the camera, then plug that into the USB. Don't forget to determine which COM port you connected the USB TTL to. You can do this in the device manager. Be careful when connecting. You must use 3.3-volt logic. The camera will malfunction at 5-volt. In my case, I set the jumper to 3.3-volt. You must have PuTTY installed on your PC. You can install it from here. I'll leave a link. Replace COM5 with the number of your USB to TTL converter. Now I'll power up the camera. The download has started. Let's interrupt the boot. Ctrl+C, you need to press this quickly. The kernel boots very quickly. You'll probably be asked to enter a password. What we entered earlier doesn't work. They say no one knows the password. We'll install the firmware in 2 stages. First, we'll install the Lite version. This will give us access to the web interface and ensure the installation is complete. Then, we'll install the FPV firmware version. Since the bootloader is password protected but not write protected, we can overwrite the old U-boot bootloader with our unprotected one. During the camera's boot process, we saw in the UART that the manufacturer also uses U-boot. I'll download the burn utility. It contains the U-boot we need for our camera. Code right arrow download zip. Download it and unzip it to a convenient directory. I'll open the console and navigate to the folder with the unzipped burn. Next, I'll check if Python is installed with the 2 required dependencies. Enter these 2 commands. Basically, I have something installed, but it's an old version. I won't update anything. I enter the following command. I've included the full path here because I have 2 versions of Python installed on my system. One of them doesn't have the required dependencies installed, so I'm entering the full path to the required Python. Now I've reconnected the camera. I can see the download starting. So I did everything correctly. Everything is fine. I got this prompt. I'll increase the font size. We've successfully installed the U-boot bootloader now. We need to download the Lite firmware. You'll need a TFTP server installed. I've included a link to the server I use in the description. Launch the TFTP server and set the path to the Lite firmware folder. Also, specify the IP address of the device the camera is connected to. I'll go to the OpenIPC website and create instructions for flashing the firmware. Here you need to enter the IP address we selected for the TFTP server. I didn't save the original firmware, so I skipped straight to the installation. Here, they offer to download the Lite version. I downloaded this firmware to the folder used by our TFTP server. After that, you can enter these commands in the POO-TTY window. The download isn't working now because I forgot to connect the patch cord. I connected it, and the program shows some kind of transfer in progress. That's it, the installation is complete. Now let's find the camera's IP address. Let's log in. Login, root. Password, 12345. Now you can enter the ifconfig command, and here you'll see the camera's internet address. Okay, let's connect to it via the web interface. The password and login are the same here. I'm prompted to change the password. Let's change it. Now we can see what the camera is outputting. Currently, there's high latency and low frame rates. We'll fix this later with settings in the FPV version. We won't be changing any settings here. After installing the FPV firmware, we may lose access to the UART. Therefore, we need to check alternative methods of connecting to the camera. Let's connect to the camera via WinSCP. Let's create a new connection, enter the camera's IP address and the username and password we changed earlier in the program, and select SCP. Now we're connected. You can open the console here. I'll enter the old ifconfig command. Everything works. Here's the camera's IP address. The alternative connection works. Now we can flash the FPV firmware without any problems. We know how to connect via SCP. I've left a link to the WinSCP program in the description. Let's flash the FPV firmware. First, let's prepare the files required for flashing. These FPV firmware files can be downloaded from the OpenIPC project's Telegram channel. I already have this firmware downloaded. download and unzip it into our TFTPD server folder. After unzipping, you should have the following 4 files. Also, pay attention to this U-Boot Universal firmware. It's also required. I couldn't install the FPV firmware with the old one. I don't know why. I'll leave a link to it. I connect to the camera as usual. I entered the following command in the command line. Remember, you may have a different COM port. I powered up the camera. Now I enter all these commands in sequence. Everything I'm entering now is in the installation instructions. Before executing the next command, I start the TFTP server. We've copied the U-Boot Universal bootloader. Now I'll reboot the camera. The main thing now is to press Ctrl+C in time. Now I'll flash the FPV firmware. We've installed the FPV firmware. Now you can see that after the system booted, the UART stopped working, as I mentioned earlier. I'll connect to the camera via WinSCP. Login, root, password, 12345. The firmware isn't finished yet. By default, the firmware doesn't support the sensor installed on our camera. Cameras with this processor are usually ordered with a different sensor, but that's not a problem. You just need to download the necessary files and copy them to the appropriate directories. We need these 2 files. I'll leave a link to them in the description. I've already downloaded them to a separate folder. Copy the SO file to the usr/lib/sensors/ directory. As you can see, 2 sensors are supported by default, IMX 335 and IMX 307. You can buy a camera with these sensors and won't need to install drivers separately. The GNI file is in etc. sensors. Now, for everything to work together, you need to set the same settings in the Majestic YAML file as in the GNI file. We need to change the frame rate and resolution. We'll also change the bitrate. Now, to test everything works without configuring the ground station, let's change the IP address here to the IP of my local machine, the one we specified in the TFTP server settings with port 5600. This is necessary to redirect the video stream from the Wi-Fi transmitter, which we haven't yet connected, to the address of the local machine, which will display the image on the screen. You must have QGround control installed. Be sure to allow all incoming connections for it in your firewall. Now, in QGround control itself, enter the following settings in the program settings. Now, I'll reconnect the camera. This time, the camera came with this useless connector. I don't even know what it's called. Maybe if the seller had written the name, I would have connected it differently. Let's grab a heat gun and quickly desolder this useless thing. I insulate everything we won't be desoldering. Basically, we can melt this connector without any problem. We won't be using it. We're now interested in where the USB pins are so we can connect our Wi-Fi transmitter. The seller's page has a pinout for this connector, J3. Here's Wi-Fi DN pin 9 and Wi-Fi DP pin 11. We'll take the positive and negative wires from our power supply circuit. The camera's built-in power supply circuit may not be able to handle it. I'll show the power supplies later. I have these USB connectors and a shielded cable. I'll leave links to them. First, I'll solder the wires to the camera's pins. I have special thin 34 AWG wires for this purpose. Afterwards, I'll cover them with UV curable solder mask. You can't leave them like this, as these contact pads can easily be torn out. Later, we'll install special wire mounts in the camera body. I'll temporarily glue them in place for security. Now I'll connect this to the cable and the USB port. I'll tie the cable to the PCB with wire. I'll solder the power wires to this port. This port is also a ZH 1.5 port. We'll use this port to power the Wi-Fi transmitter. I'll provide a link with connection instructions in the description. To power the camera, I'll be using converters installed on the Chebbuрлятор command receiver circuit. I have a video on my channel where we detail the design of this circuit. The Chebbuрлятор receives commands from the control equipment and generates control signals for the brushed and servo motors. If you're interested, you can watch the video. I'll leave a link in the description. This PCB has two terminals, plus 12 volts for the camera and plus 5 volts for the Wi-Fi transmitter. The positive terminal is marked here. The camera can be powered in various ways. If you have a 12-volt power source, you can reduce the voltage to the Wi-Fi transmitter using, for example, this circuit. I'll leave a link to it in the description. Before turning on the Wi-Fi transmitter, we need to configure some settings. We need to check that everything is soldered correctly. I'm powering up the camera and the transmitter. I entered the oconfig command. If everything is correct, my transmitter should be detected here. Here it is, WLAN 0. In addition to configuring sensor reading and generating a video stream with the specified parameters, we need to configure the video signal transmission parameters. I'll open the datasheet for the chip installed on our Wi-Fi transmitter. From here, we're interested in 3 values: guard interval 400 ns, bandwidth transmission and modulation. We'll use 20 MHz for bandwidth transmission. We'll use QPSC modulation with a coding coefficient of 0.5. I'll open the table. According to our parameters, the transmission rate will be up to 14.4 Mbps. Previously, in Majestic YAML, we selected a video stream bitrate of 4 Mbps. It's recommended to select a transmission rate twice the video stream bitrate. We can easily use modulation and coding scheme, MCS 1. Don't forget to return the IP address for transmitting video over the radio channel. Now I'll go to the WFB conf file. Here are the settings. Channel equals 165 is the frequency at which transmission will occur. Driver TX power override equals 10. This is low power for 1 watt transmitters. You can set it to 30. In my case, it says that power up to 5 W is supported. I highly doubt this figure. Bandwidth equals 20 is the value we discussed in the table. Here it is. We set MCS index to 1. We'll leave the rest of the settings unchanged. Saved the settings. Don't forget to copy the key from the camera to the ground station. I'm using Ubuntu as the ground station. We'll configure a few settings. I'll copy the drone key file to the user directory. Now let's update the system before installing the necessary packages. First, I'll install DKMS. It's needed to install the chip driver. I'll install the GStreamer right away. It'll be needed to output video to the screen. We'll disable driver updates for the transmitter chip. These commands can be used to install router drivers. Wi-Fi Broadcast Next Generation allows you to receive and decode packets from broadcasts. You need to specify the name of your transmitter in the command using the oconfig command. I connected the router to the ground station's USB port. I got this file from the channel's author, Igor Nyko. I'll leave it in the archive as well. It launches our Wi-Fi receiver into monitor mode. Let's make the setting, sh file executable. Now, before each ground station launch, you need to run this file. I enable video signal transmission and enter this command to receive and decode the video. Note that the network device name is also entered here. Now all that's left is to display the received video stream on the screen using the codec selected earlier. We chose H.265, so I use it everywhere. If everything is done correctly, you should see the camera image here. Well, congratulations on successfully setting up the digital connection. It didn't work for me the first time. I didn't get this sequence of actions right away, so be careful when setting it up. Amazing! The camera essentially reminded me of a single-board computer. I connected to the orange in the same way. It has a command interpreter, just like the orange. I'm sure you could write your own program that would run successfully on the camera and perform useful work without any issues. The camera isn't just for show. There were videos on the channel showing the operation of the command transmitter and executor. I've included a camera pan control system on this thing. I've already completed the self-propelled platform. The Chebbuрлятор command executor is installed on it. It powers the camera and the Wi-Fi transmitter. There are also multiple outputs for connecting motors. Some of them are designed for controlling the camera gimbal. We just finished updating the camera firmware today. Before installing the camera on the platform, we still need to build the camera body and gimbal. I might make a video on this later. That's all for today. Thank you all for your attention. Subscribe to the channel, turn on notifications, and see you next time.